Welcome back now on to the 22nd lecture of the course. We are roughly still in the middle of the course. We are discussing soft lithographic methods. This is the 5th lecture on soft lithography in fact. So, let us continue. We are back to this slide again, which sort of classifies the different techniques, and now let us relook into it. So, we now know firstly some of the techniques. So, we now know nano imprint lithography, we now know CFL, we now know micro molding in capillaries, we of course know replica molding, and we have also talked about another technique which is sort of very close to micro molding in capillaries, SAMIM. Just to give you a flavor how many names are there, how different techniques are present which vary some bit from the original technique. We have so now we see that we have not talked about micro contact printing, which is in fact a method for creating chemical patterns, and another technique that sounds very similar to it, micro transfer molding, but that does not give a chemical pattern, it creates topographic patterns. In fact, you will find that this technique is very special, because why it is special, let me tell you now. Because typically nano patterning results in patterns on a film or a surface. So, these are primarily 2D structures, but this micro transfer molding, with the invent of micro transfer molding, people have tried to use soft lithographic methods or nano patterning methods in a limited way for creating 3D structures. So, we will see that. I would also like to emphasize one more thing, that the classification we have had so far, topographic patterns and chemical patterns, that we understand. We also had a classification based on whether you are using a flexible stamp which can be peelable, that is the most important aspect, or a rigid stamp, that we understand. However, one more thing is written over here which I did not highlight till now, and now you are in a position to understand that, is the dynamics. This is particularly valid for the different topographic techniques. In fact, it turns out that this is also valid to a large extent for micro molding in for micro contact printing, is that the pattern replication in almost all these methods except maybe micro transfer molding, because which is a very special technique. It is just bracketed there because it also creates topographic structures. They are not 2D structures, they are in fact 3D structures, we will see that. In all these techniques on this side of the diagram, the pattern replication takes by means of confined capillary dynamics, and therefore, you typically do not apply a huge amount of excess pressure or force from outside. In contrast, nano imprint lithography is actually a brute force method. You apply a lot of force to do the deformation, and the deformation of the polymeric layer is actually a viscoplastic deformation. It is not a capillary driven flow, and that is in fact this mechanism, as I mentioned once briefly, necessitates you to use a rigid stamp, because since you are applying a significant amount of excess force to cause deformation of a softened or molten high viscosity polymer layer, you need lot of pressure to cause deformation, and unless you have a rigid stamp, you apply the pressure over a flexible stamp and the stamp is simply going to collapse, it is not going to lead to pattern replication. So, these are the issues. So, anyway, today we will concentrate or focus in this lecture on learning the process of micro contact printing or MUCP. Let us just recap quickly what we mean in the context of soft lithography as a chemical pattern, and this in one of the initial slides on soft lithography I had clearly highlighted that in the context of soft lithography, a chemical pattern typically means alternating patches of more and less wettable domains. So, how do you create that? In order to create that, of course, some of the things match very closely to other soft lithography methods, like you use a flexible stamp, Silane stamp, but you need to, in order to create this wettability domains, you need a special type of a molecule called a silane molecule. It is another type of a surface active molecule, not exactly a surfactant, because the geometry and the chemistry is slightly different. In fact, there is a lot of work that goes on in silane chemistry. I will not focus too much on that. I will just give a very brief idea about this so called silanes molecules. So, they have a structure like this. So, they have two groups. So, if you look carefully, this is the structure of a silane. This is somewhat different from a surfactant, because the surfactant has this hydrocarbon tail, but it has only one head group. In contrast, a silane molecule is sort of attached to two end groups on the two sides, and these two end groups actually have different roles to play, which you can see from this particular slide, this particular figure shown over here. In very simple terms, the group Y is sort of, again let me sort of tell you that this picture you are getting is a very simplified picture. Silane chemistry is very complicated, the self assembly process is quite complicated, and a lot of people do research on that. We just pick up the essential concepts for patterning, and therefore, I will only limit my discussion to that, what is necessary in the context of soft patterning. So, this group Y is sort of its function is to bind this molecule to a surface. So, let us say this is a surface molecule to which this Y binds itself. Now, of course, it does not bind to anything and everything, it binds to only specific molecules. Most cases silanes have affinity towards metallic surfaces. Therefore, the original paper on micro contact printing, as well as subsequently many other papers, or what you see here, people use a gold coated substrate. Of course, it works with silicon also, but mostly people use a gold coated substrate, because this Y group, I am not even telling you what is this alkyl siloxane. So, what is the exact chemistry of this Y or X group, I am not even telling you that, it is also not important to you. So, this Y end attaches to the surface. So, now the structure of the molecule is something like this. This is the hydrocarbon tail, and on the other end you have this group X, and this X you can have different types of end groups. So, you can have groups like COH or CH3, and it turns out this is acid. So, this is hydrophilic. In contrast, this is a pure hydrocarbon. So, this is hydrophobic. So, what is the consequence? Consequence is that if you have a surface like this, over which the silane molecules attach very closely, depending again on the concentration and things like that, the surface is now fully covered with a layer of these silane molecules. And what determines this covering? It is a self assembly process, just like the formation of surfactant micelles. So, you see it is a self assembled layer and it is a single layer. So, this whole process is called a SAM. This thing is called, this type of a coating is called SAM. It is what is known as a self assembled monolayer. Okay. Only thing that you need to ensure that you provide the appropriate surface vis-a-vis the appropriate silane group, the appropriate silane. Why you need the appropriate surface? Because you must take a surface to which the N group Y has a preferential affinity. If that is not there, it will not take this structure. The molecules will be simply scattered over the surface and the functionality will be lost. So, what can you say once the self assembled monolayer has formed? All you can say that now the effective property of the surface effective what property? In fact, wetting property of the surface is determined by that of the SAM molecules. At this point, you should not make a comment that, well, you have a self assembled monolayer coating and therefore, the surface is behaving like hydrophobic or hydrophilic. And why you should not jump to a conclusion? Because it depends whether the surface will effectively behave like a hydrophobic surface or hydrophilic surface will depend on the nature of the group X. So, if you have a hydrophobic silane, well, anything now dispensed on the surface, a drop of water, let us say, dispensed on the surface will not see the actual surface, but it will sort of see this N groups X. And so, depending on what type of silane you have, the surface can either behave as a hydrophobic surface or hydrophilic surface. So, self assembled monolayers are in any way, even without micro contact printing, very widely used to tailor the effective property of a surface. So, you have a surface, you need some hydrophilic property of the surface for certain application. All you do is you take a silane solution, immerse the substrate into the silane solution, take it out, let the solvent evaporate. As long as the solvent is there, the molecules will reorient and self assemble on the surface, and this will lead to effective change on the surface energy. So, this was known, but how do you create patterns with alternating patches? So, this is what you would like to achieve. What we have talked, that you have a surface with surface tension gamma s and you silanize it, that is the term. You end up having a surface which has very similar mechanical properties and all other properties, because the silane layer is only one monolayer thick. However, the effective surface energy will be reflected of that of the silane molecule. But from there, how do you get these type of pattern patches? And the philosophy that was adopted is very simple. In fact, I will just take a minute to run the. So, this movie will give you an idea about how it works. So, before I start, let me just tell you what we have. So, this is the surface that needs to be patterned, and you have a master which is nothing but a replica molded Silgard 184 stamp, and here you take the so called ink, which is nothing but a silane solution. So, all you need to do is initially you immerse the stamp into the silane solution, the stamp becomes wet. You have, in fact, you can try to recall that there is another technique in which you have used a wet stamp, and that is SAMIM, right. So, there you wetted the Silgard stamp with a pure solvent. Here, instead of a pure solvent, you are wetting the Silgard stamp with a silane solution. So, this wet part of the stamp, of course, please understand this is a cartoon I have drawn, and therefore, it shows as if only these areas are wet, but it does not happen like that. The whole stamp gets wet, and all you need to do is you simply bring it in and press the stamp against the surface to be patterned. What is the idea? Idea is very simple. Idea is, unfortunately, the movie is not working from here. Oh, it is working, great. Yeah. So, idea is that, but anyway you had an exaggerated view, which is good. When you bring in and place it in contact, so here is your surface to be patterned, and here you bring in your stamp, which is wet with the Silane solution. So, here is the critical step. So, it is actually wet all over. Right, and so when they are in contact, in fact these areas, the liquid is in direct contact with the substrate. So, ideally the Silane molecules present over these areas should bind, should get an opportunity to bind to the surface, while other areas it will not bind, and therefore you end up getting patches which are alternating with alternating wettability regimes. Whether this silanized patches are hydrophobic or hydrophilic, again will depend on the nature of the silane molecule you are using. So, if you are using let us say hydrophobic silane and had a hydrophilic base, you can create a surface with alternating wettability domains. You can also start off with a hydrophobic surface and take a hydrophilic silane to achieve the same. However, there are certain critical issues that one needs to understand, is that the viscosity of the silane solution is very, very important, and the contact time during this transfer, because what happens by the time you wet the stamp, bring it into in contact with the surface to be patterned, and if by the time the stamp has become too dry, then what will happen, there is not adequate amount of solvent to form the bridge between the stamp and the substrate, and if it is too dry, then unfortunately the silane molecules are completely stuck on the stamp surface, and they actually need this liquid meniscus through which they can sort of migrate and undergo this self assembly. But if the liquid meniscus is absent, if like the stamp comes and it is too dry, then the transfer does not take place. On the other hand, if it is too dilute, if it is too wet, right. So, what will happen, it will transfer, the silane molecules will transfer, but if it is too wet, then in fact liquid tries to drain off from these areas, and as a consequence these patterns will try to smear out, and you will get transfer, but you will get additional transfer of molecules which are beyond the width of the original stamp pattern. So, your feature size becomes large. This is not a very controllable technique. So, you can't control it, smearing is dangerous. Like you try to write with an ink pen on a blotting paper, you cannot control the width of your writing, it sort of spreads out. So, something similar, but there it spreads because of the fibrous nature of the paper. Here it tends to spread because the solvent is too wet, there is too much amount of excess solvent which is trying to spread out. And what is the danger of this technique? I mean, if there is too much drainage, of course these are small patterns, if there is too much amount of spreading, there is a possibility that the meniscus from two adjacent, so these are two adjacent tooth of the stamp, so the molecules are transferring and it is spreading, so it is spreading up to here, this one spreads up to here, they join up and your whole purpose is lost. Why? You achieve silanization, but not only below the protrusions of the stamp, you get a full coverage of the surface with the silane molecules, and therefore your whole purpose of using a patterned stamp to bring in silane molecules and bind it preferentially, the whole purpose is lost, because this you could have anyway done by simply immersing the substrate into a silane solution. There was no need for you to take so much amount of trouble. So, this is in fact micro contact printing. So, this is another schematic that tells you the details, roughly the same thing, it is a good recapitulation for us. So, now you understand this is the this is the stamp, this is the stamp, this is the Silane solution, you immerse it. So, unlike the cartoon, you now understand that the Silane layer is adhering conformally to all the surface, and therefore, the possibility, the latter possibility, this particular possibility is very high. So, therefore, this particular possibility is very, very high. Therefore, it is very important to control the drying time and the exact condition of how wet the stamp is. So, it is possible that after you wet, you might wait for some time for the solution to dry up a little bit, right, and therefore, often silanization is or micro contact printing is performed inside a glove box or something like that, which has controlled humidity, because humidity again affects it in a very big way, because even if you give the same amount of waiting time between wetting and imprinting or embossing, depending on humidity, the amount of solvent actually sticking onto the surface is going to be different. So, you transfer it, this is the inset, this is what you want to achieve. You do not want these layers to drain off and spread on your surface. So, this is the chemically patterned surface, and here are the the problems. If it is too dry, there will be no transfer. If it is too wet, there will be smeared patterns. So, now I think you understand the problems, and there is one singularity that comes out. Silane molecules, after all, even over here, they have formed a single mono layer, and their height may be is of the order of a nanometer maximum. So, question is, how do you visualize such a surface? I have not yet taught you AFM, which I will start in within just about 2 lectures or so, and then you will realize that a regular atomic force microscope imaging will not help you to achieve this. So, you need some special technique for that, which I will also cover with reference to this particular picture. So, this is something that will come up later. The last so called conventional soft lithography technique is micro transfer molding, a very elegant technique, and as I have already mentioned that this technique is capable of producing 3D structures. So, let us see what is done. You initially take a crosslink PDMS stamp as usual. You take a special type of a pre-polymer which is UV curable. So, what you do, you pour it just like replica molding, but then after you have dispensed the solution with a doctor's blade or even a simple scraper, you just throw away the excess amount of liquid that you have dispensed. So, all you have is this stamp, and this is filled up with this pre-polymer. Now, this pre-polymer is actually a special type of a pre-polymer. It is typically an UV curable material. So, we have talked about this so called UV curable materials in the context of UV NIL. So, we know that these materials solidify upon UVO exposure. So, you do that, you shine UV, I would have been better off to draw one more frame which I missed out due to whatever reason. You shine UVO. So, each of these polymer strips within the groove sort of cross links and they solidify, which is good. Now, all you do is you turn the assembly. So, these are now solid, each one of them is now solid, they are no longer liquid. You turn them upside down, keep it on a flat surface, and you would like to release them from the stamp. Now, a simple peeling of the Silgard stamp as you have done in replica molding or something like that is not going to work, because these strips are adhering too closely with the Silgard stamp. So, what do you do? In fact, you take advantage of one specific property that I have mentioned, and that is solvent vapor exposure of this Silgard block. You remember when you do a solvent vapor exposure of a glassy polymer, it starts to flow because of its reduction of its apparent glass transition temperature to room temperature or even below. But I mentioned that when you do a solvent vapor exposure to a cross-linked polymer, it fails to flow because of the presence of the physical cross-links, which sort of prevents the flow. However, since it is a polymer and you are exposing it to a solvent, a good solvent of it, therefore, you still have this liquid penetrating into the cross-linked polymer matrix, but it does not flow or it does not lead to reduction in Tg, but it leads to swelling. And this is exactly what is done. This assembly is exposed to solvent vapor where it swells, and therefore, now if you peel, so you can use chloroform vapor because chloroform swells Silgard significantly, and now if you peel it, it simply comes off, leaving behind these isolated threads on a flat surface, right. So, the most interesting part of this particular technique is these strips were made within the grooves, they were made somewhere else, and they are now placed on a flat surface. So, this is for the first time. So, this type of structure, for example, you could have created by mimic also, but the fundamental difference is that you created the structures directly by mimic on the flat substrate. You did not have a film there, you do not have a film here also, but in mimic you created the structures right here. In contrast, by this method what you have done, you have created the structures within the Silgard stamp, and you have simply placed it over here, and that in fact paves a way for creating 3D structures by means of stacking, let us say one layer after the other. So, if you can do this transfer once, what prevents you from repeating the process up to here and then straight away now place the stamp at an orthogonal direction to the initially existing structures. So, you build a second layer, you build a third layer, and you go on building your structures like this, which demonstrates that under certain conditions, and of course, there is material restriction here because you cannot work with all sorts of polymers, you can in fact use soft lithographic methods also under up to certain limited extent for creating 3D structures. So, that sort of brings us to the end of our discussion on soft lithography. I will pick up some very unconventional and new techniques that are coming up along with the advantages and limitations of soft lithography in the next class, which is going to be the next last lecture on soft lithography. Thank you.